Woohoo! Start! All right, folks, Berto back again. Video number, I don't know, what are we up to, 5, something like this? I think this is Friday's lesson, kind of recording them ahead of time, so I don't know what the heck I'm doing. Just kidding. So I think this is Friday's lesson right here. Make sure you download those dittos on my website right there. Monday's lesson, technically this is kind of like the end of the curriculum right here. Monday's lesson is really going to be no video. Okay, just you guys downloading a review ditto and working on that. As far as when you're going to be tested on stuff like that, I don't know. Like I said, I kind of want to get that take-home test going for the stuff that we did previously before school was postponed. You might be like, but Mr. Beto, that's a long time ago. Yeah, but it's a take-home test, okay? So take a look. You have all the information right there. Really just need to get in a grade for the third quarter. Once again, administration is still discussing it, so we see what happens. Anyway, hopefully you did that homework and you tried it out, all right? Number 1 was kind of weird, okay? But, fractional derivatives right here. I wrote that it's dne at x equals 0, set the denominator equal to 0. It's never equal to 0 if you set the numerator equal to 0. So usually I set these up differently now, but really the same answers. And really it was just radical x actually vertically stretched by a factor of 3, then shifted down by 1 unit. So if you couldn't do that without calculus, don't worry about it. But with calculus, should be able to handle something like that. Once again, if you're confused on these, okay, send me an email, send me a remind text, okay? If you feel the videos are working for you, let me know. Give me feedback, okay? I mean, I'm very selfish with my food as well, but you got to give me a little bit of feedback on these problems right here. We'll do the second homework problem together. Given the following f prime and f double prime lines, sketch a possibility for y equals f of x. We're not going to be able to sketch what f of x is actually equal to, just a possibility given this information. And they gave us the first and second derivative test. We know that at -2, at 0, and at 2, f prime is equal to 0, which means f, that function that we're trying to sketch, has a horizontal tangent line at those x values right there. And we know the extrema. We know there's a locum-min, followed by a locum-max, followed by, ooh, look at this. Negative to negative, that means f is going to go from decreasing to decreasing. So decreasing, level off to a slope of 0, continue to decrease. First time we saw that, okay? We always saw alternating lines. It's not always going to be that way. Also, endpoint extrema, if a function starts and immediately decreases, has a negative slope, endpoint max. If a function decreases and then stops, endpoint min. And the second derivative test, you don't need to set up that that dummy sketch, sorry. You could just actually set up where there are inflection points. Make sure you look to see where f double prime changes sign, which it does at all of these values right here. So those are all inflection points. It says sketch a possibility for f. We don't know what f is, okay? So we can't get those y values, so we just have to be intelligent in the way that we pick them. But we do know it goes from -4 to 4. So I'll draw my x and y axes that I love to the maxi and start at -4, a 1, a 2, a 3, a 4, and end at a +4, a 1, a 2, a 3, a 4. And now when I plot points, okay, think about it. I have endpoints, I have critical points, and I have inflection points, okay? They all need to be graphed. I'll graph the endpoints first, I'll just go from left to right, to be honest, on the first derivative line. At -4 comma something, there's a point. We don't know what the something is because we don't know what y is equal to, but the function is going to immediately decrease after that. So don't plot like -4 comma -50, because then your graph's going to be all the way down here. Be intelligent about it. -4 comma something up here, I'll say. And now you got to, really think about this for a second. If you go to -2, the function has to decrease from -4 to -2. So you can't plot -2 comma something higher. You got to plot -2 comma something lower because the function's got to decrease to get there. Don't put it right here. I know it's lower, okay? But the more spread you put between the points, the more happy of a graph that you will have. It'll be easier for me to grade it and for you to actually do it. So I don't know, maybe -2 comma something down here, right? Maybe something negative. Then we increase until we get to 0 comma whatever. Okay, so increase until we get to 0 comma maybe this y value there. Then we decrease when we get to 2, and then we decrease again. So don't at 2 put it all the way down here because we got to decrease again. So let's say we decrease and we get, hey, how about it's a 0? Why not? Why not? Y sub 0? And then maybe we decrease again to get to x equals 4. See, now I know the function is decreasing, increasing, and decreasing, just like my line says. Inflection points have to be in between. There's an inflection point at -1. You can't put it here, because the function has to increase from this point to this point, so it's got to be somewhere in between. To get the nicest sketch, if you imagine that this is a straight line, and then you put the point where it would be if it was on that straight line, that'll give you a better sketch, an easier sketch. You could obviously have it anywhere in between, but it's useful. You know, another inflection point at x equals 1, so in between these points, imagine that was a line right there, and this right here would kind of be on that line, makes it a little bit easier. And another one at x equals 2, which is kind of cool because we already have that plotted. This dude does double duty, okay? You know, right here, it's a critical point, also an inflection point, okay? Don't you see how it changes from a U to an N, how concavity changes? So it should kind of make sense. Now when we sketch this, okay, I'll just use the second derivative line for N's and U's because I already know about increasing and decreasing up here. I have it plotted. Decrease, increase, decrease. And I know that the function looks like a U from -4 to -1. Really enunciate that, okay? So we know from -4 to -2, it's decreasing, but it decreases looking like a U. Really enunciate that U so I could see it. Should make sense, right? Because you want that local min right there at -2. Now it's still a U until you get to -1. So it decreased like a U. Now it's going to increase like a U. And now it's going to look like an N, concave down, from -1 to 1. So I know it increases looking like an N, and then it decreases look like an N. Go point to point. Don't try to do it all at once, because then it's difficult to do. But you can see that local max right there. There's that inflection point. See how it changes from a U to an N right there. Speaking of inflection points, we just hit another. We look like a U from 1 to 2. So decrease looking like a U. And now you're not going to start increasing. It's not a local min. You're going to continue to decrease, but you're going to look like an N now. So you can kind of see how the graph has this anomaly going on over here, something that we haven't seen before. And this is a possibility. You know, your graph could be shifted up, it could be shifted down, it could be stretched, okay, a little bit more than this one, but try to do the best you can. I know that sketching is difficult, but it will come in time. Try to go point to point. You know, what I'd like to do now is a couple of practice problems, some interesting types of problems. So you should have a packet, okay, that you downloaded. You know, I think this is lesson number, where's my piece of paper? Oh, I don't have it right here, but I think it's lesson number 1.5. Anyway, hopefully it's easy to follow on my website. So here we got a few problems. Okay, and some of them are a little bit different. You know, not every problem they could ask you to do, where are the critical points? Where's the function increasing and decreasing? Extrema, you know, concave up, concave down, inflection points. They're not going to have you do that for every single one. Sometimes you're going to have cool, you know, conceptual types of questions. We'll do 1, 2, 3, and 4. And your homework will be to finish the ditto and hopefully thoroughly enjoy the process. So let's take a look at number 1. Classic problem, shows up on AP exams. I've seen it before. The graph of the function y equals f of x is shown below. Whoop, there it is. And they want to know in which of the following intervals is f prime positive and f double prime positive. So they're really asking you, giving you information about f of x, but they're asking you about f's first derivative and f's second derivative. And think about how f's first derivative relates to f. It tells you the slope of f, whether f is increasing or decreasing. This is saying f prime is positive right here. If f prime is positive, that means the slope of f is positive, the rate of change of f is positive, the y values of f are getting bigger, f is increasing. But if f double prime is positive, does not necessarily mean that f is increasing. That means that f is changing at an increasing rate, okay? So this is actually f concave up, okay? So you just really want to look for the times on the graph, the intervals where f is increasing and f is concave up. If you're increasing, you're going up. If you're concave up, you look like a U. So if you're increasing, concave up, you're going to look something like that right there. So really, you just want to see where the graph is doing that. From A to B, the graph is concave up. It looks like a U, but it's decreasing, so that's no good. From B to C, this is what we want, okay? The graph is increasing, looks like a U, so no A to B. B to C is good right here. From C to D, the graph is increasing, but it's concave down. Not interested in that either, okay? So 3 only right here as far as the problem is concerned. Not a terrible problem. It's conceptual. You got to think about it, okay? Hopefully I'm not moving too fast with these videos. But remember, if you hit pause and you come back, we'll be right here. You know, take a look at number 2. Number 2. Got to get some jokes going. This is cool, okay? Because look, you know, a lot of the problems we've been doing were functions represented, you know, algebraically, right? They give you the algebraic representation for a function, want you to eventually sketch it. The last problem we did, they actually gave you a function represented graphically, and now they give you a function represented tably, which is really numerically. That's the way you're supposed to say it. But they say various values for the derivative f prime of x of a differentiable function f. So that just means you could take the derivative. It's differentiable everywhere. It always has a slope. Also means it's continuous everywhere. Are shown in the table below. They tell you if f prime of x only has 1, 0, which of the following statements must be true? F prime of x only having 1, 0 is actually pretty important. That means this is the only place where f prime is equal to 0. Too many people, they look at these charts and they're like, yeah, it's telling you exactly what's going on with the function. It's not giving you much information at all, okay? It's just giving you a list of separate points. It's not telling you what the heck is going on between 1 and 2, but at least we know that the derivative will never equal 0 between 1 and 2, so it can't suddenly become negative between 1 and 2. It has to remain positive. Also, no funny business, no discontinuities or anything like that, because the function is differentiable. You could essentially ignore that information and still get this problem, right? But that's because this is a pre-AP class. In an AP class next year, they will mess with you with stuff like that. So you need to be careful. You know, and they only give us information about f prime. So when you look over here in A, they start talking about f having a relative minimum. That is the first derivative test. So that could be possible. But then they're talking about f changing concavity at x equals 3. That's an inflection point, okay? F prime is not going to tell you about inflection points. That's f double prime's job. It could tell you about maximum. So C is a possibility. D, it ain't going to tell you concave up. All right, because that's the second derivative's job, okay? So you can knock that out right there. And then they want to say the graph of f of x is symmetric with the line x equals 3. Well, you need to know about the y values of f, and f represents the y values of f, not f prime. F prime represents the slope of f. So believe it or not, you could really narrow things down here to A and C. And now you're like, oh, relative min, relative max. I mean, surely there must be some sort of test. And there is, the first derivative test. That's where I draw the line. The f prime line. Is it bounded? Some people say yes, but we don't know. They don't tell you that f only exists on the closed interval from 1 to 6. That's the information they gave you, but I have no idea if it's bounded or if it's unbounded. It doesn't matter, okay? They're just worrying about what happens at x equals 3. And at x equals 3, you can see by the chart, that's a place where f prime is equal to 0. That means that f is going to have a horizontal tangent line, which means it could have an extrema, okay? You know, remember, at a horizontal tangent line, you could be decreasing to decreasing or increasing to increasing, which means there's no extrema. But because of the multiple choice selections I have left, I know there's going to be one of the extremas here. People are like, well, how the heck are you supposed to do this? Well, pick a number to the left of 3. I don't know, 2. What do I do with that? Well, you plug it into f prime. Here's the f prime line. Well, you don't even have f prime. How can you plug a 2 into it? It's right here, Poppy. F prime of 2 equals 4. 4 is positive. You know, maybe plug in x equals 4 right here. If you plug in a 4, you'll get a negative 4 back, negative. And now we have our line. We know if f prime changes from positive to negative, that means f changes from increasing to decreasing. And that means we have a relative maximum at x equals 3, which you could ascertain just by looking at this chart up here and be like, yeah, at x equals 3, the derivative changes sign from positive to negative. Only because there's only 1, 0, okay? It's possible in between 2 and 3 that the derivative could change sign if it didn't tell you that there was only 1, 0. Once again, we'll speak about stuff like that more next year, but hopefully not too terrible of a problem here. So, you know, some cool, like, conceptual problems there, you know, kind of like eloquent. Number 3, pretty classic situation. You know, I'd be like, hey, I think this would be a good problem to put on a test. That's what I normally say in class. A lot of these tests are probably going to be take-home tests anyway. So, you know, we'll see what happens with stuff like that. But a great problem right here. At what x value does this function right here attain its absolute minimum? You know, if you want a minimum, I mean, you know, they're not going to make you do everything like we did before. Let's just focus on the first derivative test. Surely there must be some sort of test. The first derivative test, which means we got to take the first derivative. So I'm going to derive. I will derive f prime of x equal to 3x squared minus 3. It's always existent. It's polynomial. Let's set it equal to Mr. Pushy's IQ. Factor out of 3. Could divide by 3 on both sides. Get a little difference of 2 perfect squares action here. Factor it up. T it up. And you'll see x equals negative 1, x equals 1. Critical x value. Some people are like, oh, let's write the critical points, plug into the original. No, okay? Look, I just want to see where there's minimums here. So that's where I draw the line. The f prime line. Tis it bounded? Yes, it is bounded. So important with absolute extrema that you check those endpoints, okay? You can have extrema at the endpoints. We spoke about stuff like that A lot of people leave that out. If there's multiple choice, they'll just pick the interior point that satisfies a minimum when you have to check those, points on the, it's not really the exterior, but the point that separates the interior from the exterior. Put all critical x values on the f prime line in numerical order. We know that f will have a horizontal tangent line at -1 and 1. We like to draw that, get that little dummy sketch going so we can see if it's a max or a min. Plug back into f prime. I'll go with this version. Technically it's missing the 3, but multiplying by a positive 3 won't change sign. Plug in a -2. -2 plus 1 is going to be negative. -2 minus 1 is negative. Negative times negative is a positive. Once again, it is going to switch sign to a negative here, but that doesn't always happen. It's really, you have to have something like a double root, x plus 1 times x minus 1 quantity squared for you to get a plus and a plus here algebraically. But you can see how they could do it to you by just giving you this information that we did earlier. So just always be on the lookout for stuff like that. The signs don't always alternate. Plug in a 0. 0 plus 1 is positive. 0 minus 1 is negative. Positive times a negative is a negative. And then if you plug in like a 1.5, technically, you could plug in a 2 because normally there'd be an arrow on this thing if we didn't restrict the domain. But anyway, a 1.5 is safe. 1.5 plus 1 is going to be positive. 1.5 minus 1 is also positive. Positive times a positive is a positive. So look, at -1, there's a max. But I don't care about that at all, okay? I only care about where the function has a minimum. So I don't care about -1. Man, I care about 1, okay? Because that's a local min right there. I don't know if you can hear my 2-year-old screaming and yelling upstairs. Life in quarantine. Anyway, well, one of the biggest mistakes on this problem, by the way, is people reading the word minimum as maximum. It's not the same thing. It's the complete opposite, but it's easy to make mistakes like that. Don't forget about endpoints. At -3, we know that we have an endpoint minimum because the function starts and immediately decreases. So I care about that. I don't care about 2 because the function increases and then stops. That's a max. So I have 2 mins, okay? They want to know what x value does this function attain its absolute minimum? What x value right here? Well, I know we got mins, and I know they occur at x equals -3 and x equals 1. Remember, you need the y values, okay, to compare these y values to see which is the absolute min. Okay, so let's actually do -3 comma f of -3. Always plug into the OG function to actually get that y value. Plugging in 1 is a lot easier. Let's avoid plugging in -3 for now. We have to do it in a minute anyway. But plug in a 1. 1 cubed is 1 minus 3 times 1, which is 3. 1 minus 3 is -2 plus 7 is 5. Okay, the number of Chipwiches I ate last night. Here, plugging in a -3. Kind of annoying, okay, but look, you got to practice mental math to get good at it. Cube in -3. Remember, if you cube a negative, it remains negative. 3 cubed is 27, -27. -3 times -3 is +9 plus 7. I mean, this is kind of a cool way to do it. You could take a -27, combine it with a +7. Remember, always take the sign to the left there. -27 plus +7, that's -20. And then plus 9 would be -11. So lots of different ways to come up with it. And now look, you can see we're comparing y values, and we want to see which one has the lowest y value. And you can see the lowest y value right here is -11. So that means we have our absolute min at x equals -3, which is what they wanted to know, okay? Sometimes they'll actually not ask it, what x value does the function attain its absolute minimum? They'll say, what is the absolute minimum of the function? And remember, x values tell you where, y values tell you what. So if they actually want to know what the absolute minimum is, well, then they actually want to know the minimum y value of the function. So technically the min value is actually f of -3, which we know is equal to -11. So it's another way to ask that question when they actually ask you what's the minimum value of the function. They might even not say the minimum value. They might just say, what's the minimum of f? And if they want to know the minimum of a function, remember, a function represents y values. They want the minimum y value. So lots of different ways it could be phrased. Here they just want to know where the minimum y value occurred. Take a look at number 4, last problem here. The first derivative of a function f is given by this guy right here. We want to know the x-coordinates of all points of inflection of the graph of f. And it's important they said of the graph of f. Technically, you could find points of inflection of the graph of f prime. You just take the second derivative of f prime, which would be f triple prime. They don't really ask stuff like that, but technically they could. In that vein, by the way, points of inflection, surely there must be some sort of test And there is, okay? We know it's the second derivative test, so I need f double prime. Some people don't even read here. They're like, yep, gotta take two derivatives. No, you don't. Just take one derivative. We already have f prime. Take the derivative. 4 times 3 is 12. Raise x to the 1 less. Minus 3 times 12 was that 36. X squared. So there's a second derivative right there, marginally annoying. But look, I got to see where it's equal to 0 or non-existent. It's never non-existent. It's polynomial. Set it equal to 0. I'd factor out a 12x squared here. Makes things a lot easier. Tee it up. Don't forget, you're setting 12x squared equal to 0. You're setting x minus 3 equal to 0. Everybody knows you get x equals 3 over here. Make sure you realize you get x equals 0 over here. And some people, they'll stop right there. And they'll be like, yep, I got my answer. F double prime is equal to 0 at 0 and 3. Must be inflection points at 0 and 3. No. Okay, you have to make sure that there's a sign change. Remember, critical points, it's all about the first derivative being equal to 0 or DNE. After that, you're done. But inflection points, it's about the second derivative first equaling 0 or DNE. Then there must be a sign change in the second derivative. That's where I draw the line with you people. The f double prime line. 'Tis it bounded? 'Tis not, okay? F prime is polynomial. F double prime is polynomial, implying that f is polynomial, implying that it has domain, all real numbers. Put all possible inflection x point values on the f double prime line. We want to see a sign change, and here's where stuff gets crazy. Bananas. The math is bananas. B-A-N-A-N-A-S. This 12x squared, he's always positive. You can even slice out the 12 if you want to, right? Divide by 12 on both sides. X squared is always positive unless x is equal to 0, which it won't be. That's one of these values right here. If you square a negative, it's positive. If you square a positive, it's positive. So really, you just need to worry about this. Plug in a -1. -1 minus 3 is going to be negative. Plug in a positive 1. 1 minus 3 is negative again. Plug in a positive 4. 4 minus 3 is positive. Remember, you're just multiplying these by a positive number. That's why you only have to worry about this bubble right here. And you might notice there's no inflection point. Okay, at f double prime right there, x equals 0. But at 3, we can see there is a sign change, so we have an inflection point. So that's why we know it's at x equals 3 only, which means that A, Fonzie's favorite letter, A, is the answer to this problem here. Some people are like, what the heck does that look like? Like, how could you have a function be concave down and then concave down again? There's a lot of different things that can happen, but concave down to concave down, you could even have a local maximum right there. Maybe it's concave down and then concave down again, right? Sometimes you'll see it be concave down. Maybe it doesn't change from increasing to decreasing. I'm trying to come up with another example here. Having trouble with that. Concave down, concave down. So maybe it's concave down, then concave down again. So maybe it's this type of situation with a sharp point. So you don't always have to have a change of concavity if your derivative is 0 or if it's non-existent. But those are things we'll worry about at other times, okay? So, hopefully you can do those problems. The other ones are kind of pretty basic here, okay? Great problem number 7 right here. Classic problem right here, just like one that we already did. Is that it? There should be more homework problems. Relative minimum shouldn't be terrible either. So do the best you can. Obviously, no calculator here. Get on my remind, okay? I have to get ways to get assignments from you. I want to make sure you guys are okay, too. Trying to track students and make sure you guys are all right. You have everything you need. So anyway, get back to me if possible. Have a lovely weekend, okay? You might look at the bottom of the website today, or on the website, it might say that there is that take-home test posted. I'm planning on posting it. I'm just not I have to go back to the school to get some things, and that's not going to happen until Friday, today, between like 10 and 12 p.m. So I'll probably end up posting it a little bit later in the day, but be on the lookout for that, okay? And look, don't freak out if you're like, I can't print and da-da-da-da-da. Do the best you can. If you can't print it, you can at least write out answers, take a picture of that and send it to me. Do the best you can, okay? We'll figure out how to do it. And just don't worry about it. Stay healthy, stay safe. And, see you guys next week. Monday, you'll just be working on a review ditto, but Tuesday, starting a new chapter, okay? We got to rock and roll through curriculum. So take it easy, everybody, and we'll see you next week. Adios.